Alrighty. I think we are about ready to get started here. I got, I've got two of you in the chat. Um, if you're there, say hi so I don't feel lonely. I'm gonna get started here in just a few minutes. Just gonna hang out and talk for a bit, as has been our routine. We are going to be doing the second half of the GRE problems for this week, or of the second week of the University of Chicago online ones that we have been doing. Um, Sorry I didn't stream yesterday. I know I've been off schedule all week, but yeah, stuff happens. I got food poisoning, so that wasn't great. But feeling better, ready to stream, ready to do some math, you know, hang out with you guys. But figured I'd just chill here for a second. Just to let you guys know, because I know some people watch the VODs also, but I am going to be trying to do. Sorry, I got distracted by the iPad. I'm going to be trying to do like some alerts, like I'm thinking of doing like a super chat like donation bar if that's doable, or at least like so if you send money it like pops up with your name on the screen, just stuff that makes the stream experience better. I'm going to try to have that done by this weekend for Monday stream. Forgive my light in the background. It was behaving all day today, but of course it starts blinking right when I start streaming because nothing's allowed to go right. Um, but yeah, I'm going to be trying to improve the streaming experience as we go. I think this will be the last stream with like the not so fancy stuff. So we'll see. I had tried to have like scenes on OBS where you can like there's like a transition where it like fades through when I switch between like me and like the problems and the iPad, but when I did that it was messing with my face cam software, so I'm not really sure if I'll do that or not, but I'm going to try to get it as fancy as I can and hopefully give some better content, for the viewing experience in terms of just a little more professionalism with my streams. But I mean, these first 2 weeks have been me learning just as much as it's been anything else. So I've been testing software, getting used to being on camera, doing math, and doing the problems, and fitting it into my schedule and all that fun stuff. So I'm hoping I can start the refining process after this week, and then hopefully have good stuff going. But I think I will start doing the problems here. It doesn't seem like we're gonna have too many more people come in. Haven't seen anybody in chat yet. You could be first. It's your chance. Whoever types can be first. That's powerful. You have a powerful opportunity right now to be the first to type in chat. Alrighty. I'll go ahead and link because I was informed last stream that you guys can actually see like the chat replay as it goes. Did I close? Oh no, this is the right one. It's just scrolled up too far. So yeah, hopefully you guys can see that link for the rest of the stream. Let me link that for you. We are doing week 2. Hello, Gangsta Goose. So we're doing week 2 here. We're doing problems. It'd be, 12 through 22? Yeah? Second half. So you can follow along if you would like, but if you don't particularly want to, look at it, that's fine too. So let's get into the math. That's why you're here, right? That's why I'm here. Do some math. Have some fun. I might try and talk a little more in between problems because I feel like when I just kind of put my head down and do math, it's not as like entertaining for you guys. I mean, maybe it is. I don't know. I might try to break it up a little bit, but anyway. So let's look at the first problem. Oh, big yawn to start. Okay. So we want to consider the function f, which is a function of x and y, which is equal to x squared plus y squared minus 5/8, and that whole quantity is squared. Excuse me. With the constraints that x plus y is equal to 1 and x and y are greater than or equal to 0, and we want to verify the validity of these statements here. So we have f achieves a local maximum at x equals a half, y equals a half. It achieves a global minimum at x equals half, y equals half. and that the minimum of f is positive and that f is strictly less than 1/8. So I'm going to go about this kind of like in a simple way. You could make a table and like test where all the local maxes and mins are, but I'm just going to kind of disprove 3 of these, and then the last one will be the answer because it's faster, I think. So to start with, let's check a few of these here. So I'm going to try a few values to check some of these statements. So I'm going to start by, I need to show you my iPad here. I'm going to start by letting, so let's see, let's let x equal 1. And if you remember, the statement is that x plus y must equal 1. So that means y is equal to 0. So that will give us, for our value for our function, f of 1, 0 is equal to 1 squared plus 0 squared minus 5/8 quantity squared. And we can see that this part is going to give us 3/8 in here. And then we can square that to get 9 over 64. Now, if we go back to our answer choices here, one of them says that f is strictly less than 1/8. And of course, 9 over 64 is greater than 1/8 because 8 over 64 is 1/8. So we've already disproved that fourth condition right there, which is great. So next, we're going to want to check a different condition. So let's check and see. Let's see, which one do we want to do? Okay, yeah, so let's mess with the function a little bit and see what we can disprove. So we have the equation x plus y is equal to 1, but that means that y is equal to 1 minus x, which means we can write our function as a function of x and 1 minus x and get... I'm sorry for the yawns, guys. I am quite tired today. And we can get, let's see, it would be x squared plus 1 minus x quantity squared minus 5/8. That whole thing is squared there. So let's see what this is going to be here. This is going to be x squared minus 2x plus 1, which will give us, for our function, we'll have 2x squared minus 2x plus 1, and that's all, and the minus 5/8. So let's go ahead and just do that now. That'll be plus 3/8. And that whole quantity squared. So that's our function. So let's go ahead and try and find the zeros of this. So we can do that using the quadratic formula. So we'll have that x equals negative b, which is negative 2. So it'll be 2 plus or minus the square root of b squared, which is 4, minus 4 times 2 times 3/8, all over 2a, which is 4. So we can see that this 4 and this 2 and this 8 are going to cancel, and that will leave us with 4 minus 3 inside of that square root. So what will that give us? That'll give us 2 plus or minus the square root of 1, which is 1, all over 4. Okay, can you guys see that? Yeah, I didn't cut it off. Okay, so let's go back to our conditions here. So we have that f achieves a local maximum at x equals 1/2. And f equals, f achieves a global minimum at x equals 1/2, y equals 1/2. Let's see, am I missing something? One moment. Forgive me. What am I doing? What am I doing? I can't even read my own notes. This is tragic. I blame fatigue. Give me 1 second. This is a study stream after all. I guess I am showing that. Let's see. What was I trying to do? I'm trying to verify the maximum and minimum. But yeah, so let's go ahead and these are places where the function equals 0. Oh my gosh. I'm dumb. I'm sorry. Here we go. Yeah, one of these is that the minimum of f is positive. And I've just proven that there are zeros to the inside of this function, which means that the function can equal 0, which means the minimum cannot be positive. I don't know why that didn't occur to me, and I didn't write it in my notes, but anyway, yeah, excuse me. So these are the values, let's see. Actually, hold on, let me just write this out here. So these are the values when the inside is 0. So the minimum is not always positive. Okay, so that disproves, I believe that is condition 3. So by the two things we've done here, we've disproved 4 and 3. So now we need to disprove one more. Oh no, we don't need to disprove one more. Because if we plug in, see, the second condition is that f achieves a global minimum at half-half. And so if we can prove that 1/2 is greater than 0, then that condition is false and we're left with 1. But we can see that if we square, if we have x squared, if we have x equals to 1/2 and y squared equals to 1/2, we will have inside of our parentheses, we'll have 1/8 plus 1/8 minus 5/8. No, it's 1/4. 1/4. I don't know why I said 1/8. I got the 5/8 threw me off, I guess. So we got 1/4 plus 1/4 minus 5/8 quantity squared. But 1/2 is not equal to 5/8. So when we square that, we're going to get something positive, which means that it's impossible for the global minimum to be at 1/2, as we've just proven that there are values where the function is 0. So from here, from this statement and this statement, we've disproven number 2. With this statement here, we've disproven number 3, and with this substitution here, we've disproven 4, which leaves 1 to be our only answer choice, and I believe that is answer choice A. So that finishes off this problem number 12 here. So let me scroll down to the next one, which is number 13, and I'll get a new page on the iPad here. So we want to let C be the cylinder bounded by x squared plus y squared equals 9 and z equals 0, z equals 5. If f of x, y, z is equal to 3x y squared negative 2z squared, we want to calculate the flux of f through C, which is to say integrate the normal vector dotted with the field over the cylinder. Okay, here, let me check chat before we... Well, this actually isn't centered. Hold on, it's actually cut off, isn't it? Let me fix that for you. There, that's a little better. Okay, let me check chat before I get into this next problem. We have more of you in here? We got 6. Looks like we've only had 2 in chat so far. It's going to be a quiet stream, but that's all right. Okay. So for this problem, we're going to, so let's go ahead and write out what this is going to be. So we have the integral, the formula we're going to use is we have the double integral over s. I'm trying to do better with that circle there. It looks better. Of f dot ds is equal to the integral over ds of the curl, I believe that's the symbol for curl, cross f. So let's go ahead and calculate that curl cross f. So we'll have this table here. Have I, j, k. And if you remember how this is set up, we have to put our partials underneath that. So we'll have partial with respect to x, with respect to y, with respect to z. And then we have our given f, which is 3x y cubed and minus 2z squared. But because we don't have any terms with more than one variable, that is just going to give us 0, 0, and 0, which means our answer is just 0 because this part here is 0. And when you integrate 0, you get 0. So that is an answer, and that is going to be answer choice C. So that was a pretty easy one, given that it goes to 0. Alrighty, so let's go ahead and move on to question number 14, which if I remember correctly is also deceptively easy. Let me just number this for my own note keeping for later. Get a new page. So number 14. So I'm going to put this on the screen. I will use the iPad very briefly for this example, but it's more of an explanation type problem. Let me scroll down here so it's good to look at. Okay, so we have the hypercube graph Q sub n is the undirected graph with the vertex set, or with vertex set v is equal to 0, 1 to the n, and edge set where e is equal to v and v prime, such that exactly 1 bit of v and v prime is distinct. So that sounds quite scary, right? Unpacking those definitions a little bit, the vertex set is like an n-dimensional, like 0, 1 in every direction, and the edge set is basically just lines between them, such that exactly 1 bit, or in the computer sense, like a 0 to 1, is distinct between the edges. And so we're saying if n is greater than or equal to 1, so we're dealing with 1 dimension and up, then which of the following statements is false? So we have a bunch of things here. We have Q sub n is connected. We have Q sub n has a Hamiltonian path, which is a path that visits each vertex exactly once. Q sub n has 2 to the n times n edges. Q sub n has 2 to the n vertices, and Q sub n is 2 colorable. So that sounds very intimidating, right? But let's look at a one-dimensional example of this and then go back to our answer choices. So one-dimensional will just be on like a number line. We'll have here where this is 0 and this is 1, and we'll have one edge between the two of them, like that. This is a Q sub 1. Okay, so let's go back and look at our answer choices with this number line kind of idea in mind. So if you look at answer choice C, it says that Q sub n has, it says Q sub n has 2 to the n times n edges. Okay, so let's go back to our picture. So do we have 2 to the 1 times 1 edges? No, we don't. We have one edge. So in the most basic example here, this statement C fails because um, you can't draw another edge without violating the stated definition for our hypercube graph. So we fail answer choice C out the gate. You can't even. It's a non-starter problem. It's just C is false in every case. So for 14, the answer choice is C. And if you want, just for fun, you can look through some of these definitions and explore the ideas. I did when I was going over the problem because you don't immediately see that kind of thing when you start the problem. Like Hamiltonian path is fun to draw when you go, like even just with the three-dimensional graph, but thinking about it mathematically is very interesting. But you know, just maybe for fun, you could go back and like play with some of these definitions and just kind of explore this kind of space or this hypercube graph space, just to see why the rest of these are true. That's probably the harder question. But anyway, let's move on to question number 15. And let me check the chat really quickly. Yeah, it looks like chat's dead, but we have, so we've got some viewers. All right, so we have two ladders. This is just a simple related rates problem. We have two ladders of length 10 and 12 respectively in a small enclosure of total width 16 meters connected at the bottom in that arrangement. So if the right ladder slides down the wall, then the left ladder slides up the wall. And we want to know if the ladder of length 10 is 6 meters up the wall, sliding down the wall at a rate of 2 meters per second, at what rate is the ladder of length 12 sliding up the wall? So let's go ahead and draw this. For those of you who have seen my previous streams, you know I like to draw things for problems. So let's go ahead and make a drawing of this. I'm going to be copying it from my notes so that I don't have to like flash between the windows. So we've got this box here that these ladders are in. And we've got one that's up here. We're going to go ahead and label our points as we go so that when we talk about these figures, we can kind of like know what we're dealing with here. This is going to be our first ladder. We'll say it goes from A to C and then call this corner B. And let's go ahead and draw that line there. Actually, I think if I do this, it'll color it in for us. Yes. Okay, and then this has a length of 10, side length of 10. And then we have over here, we have another ladder. We'll call this point E, and call this corner point D. That attaches down here at C. And it has a length of 12. And we know that this whole thing here, all the way across, oops, wow, I thought that would give me a straight line, but it just didn't want to, did it? This whole thing is 16. Oh, and one last thing, we have that this length here is 6. And we have this ladder sliding down, so the d, we'll call this y1 over dt is 2 meters per second, I believe. I don't think the unit matters, but it's 2. Yeah. So we have 2 meters per second. I just probably made engineers mad by saying units don't matter. But in this problem, they kind of don't. Okay. So to start with, let's solve for our unknown side lengths. That sounds like it'll be good, right? So we will have that. So let's start with, we'll have CB. And we want to solve for that using the, I'm sorry for yawning so much, guys. The Pythagorean theorem. That'll be equal to the square root of 10 squared minus 6 squared and that is going to be equal to 8, as 100 minus 36 is 64. So that makes this length 8. Kind of slide this in here if we can. And because the whole length is 16, that means we have a length over here for this one, which is also 8. Even though I didn't draw it very well to scale, they are kind of equidistant. And then we can once again use the Pythagorean theorem to find our initial condition for ED, because these are only initial conditions. Once the ladders slide, they will move, but we're trying to calculate at what rate they move. And I believe, yeah, we just want to find the rate. We don't need to do anything with it. Okay, so ED, at least at our initial condition, is going to be equal to the square root of 12 squared minus 8 squared, right? And let's see, 144 minus 64 is 80, so we will have the square root of 80 for ED. So now we're going to want to set up an equation to relate our, here let me go ahead and draw up here what I mean when I say this. I don't really have a lot of space there, let's see. I guess I can draw it up here maybe. Let's draw it up here. We have, we want to find what dy2 dt is. That's what the question's asking, is what the rate of the second ladder sliding up is as that ladder slides down at 2 meters per second. So we want to be able to relate our y2, our changes in y2 and y1. So let's go ahead and do that and set up an equation between these two variables. So now that we have all these relations laid out, we can write a formula for y2 using our side lengths. So we'll have that y2 is equal to the square root, oops, that is not my best work there, handwriting wise, square root of CE minus dB, did I say that right? dB minus BC, yeah, squared. Keeping in mind that AB is equal to y sub 1 and ED is equal to y sub 2, because those points move with the ladders. So let's go ahead and plug in, we're going to do this so that hold on, am I? dB minus BC. Yeah, okay. So let's go ahead and plug in for our values here. So we'll have that this is equal to the square root. Well, we know that CE is 12. Did I write this down wrong? Oh, let me check chat, see if you guys have said anything. Did I make a mistake here? I think I made a mistake. I did make a mistake. This is supposed to be squared also. Okay, yeah, so CE squared is 144. And then we will have that is minus, and dB is equal to 16 minus, and we can write BC using the Pythagorean theorem as the square root, I'm going to make that square root better, the square root of 100 minus y1 squared. There I'm just not writing them as squares, I'm just going ahead and squaring them out. So that's equal to y2. So now we have an equation between y2 and y1, and we are going to want to take the derivative of these two so that we can compare the rates. And since we have initial conditions, we can solve for our dy2 over dt by plugging them in once we have solved for what we need to solve for. So before we do that, let's go ahead and square both sides to get rid of so we don't have a nested radical there. So let's have y2 squared is equal to 144 minus 16 minus that square root there. 100 minus y1 squared, like that. Alrighty, so we're going to have to use quite a bit of chain rule here when we take our derivative. So we're going to want to take d over dt of both sides. So I'll write that, and then I will actually do the derivative on the next page because we are running out of room here. But I'm just going to indicate on this page that we are going to be taking our derivative of both sides. This whole thing here. Oh dear. Oh, and I'm covering up the math here. 16 minus, let me just write it a little higher. Does that work? Yes. 100 minus y1 squared. Okay, so let's do that derivative on the next page. Alrighty, so taking the derivative of the left is really easy. We will have 2y sub 2 dy sub 2 dt. And that is going to be equal to, well, if you remember, we had a 144, so that's going to be equal, that's going to go to 0. And then we are going to have, let's see, the derivative of that big thing there. Let's see what that was. 16 minus that square root. Square root of 100 minus y1 squared. So this is also going to go to 0 right here. So that will give us, so all we have to take the derivative of is this thing right here. So let's see what that will give us here. I'm going to go ahead and turn to the next page of my notes because I'm running out of notes on this page. Okay. So that will be 0 minus, is that right? Let me look at the last page of my math here. Yeah, so it's minus, and then the derivative of that term, we need to use chain rule, so that is going to be, excuse me, man. I've been yawning a lot today, haven't I? So that will be minus 2 did I do this wrong? It will be do I need to let me check the chat. What'd you say? Have people already solved the problem in the chat here? Let's see. Let me bring up the problem again. I don't think I can do this. Can I just bring this inside? Am I doing derivatives wrong? Somebody correct me in the chat. I don't know if I can just make that go to 0 right away because the chain rule, right? Let me see. What did I have over here? Oh, did I mess up squaring it? No, I didn't. Because the whole thing was in the radical, right? Yeah. I don't know. I have something weird in my notes. Did I just do it wrong in my notes? Let me check chat again. You guys yelling at me for doing simple stuff. U to the 1/2. I'm just going to write down what I have in my notes. So we'll have minus 2 times 16 minus the square root of 100 minus y1 squared times the derivative of the inside. Oh, hold on. Oh, yeah. Hold on. I dropped something. I dropped this. Oh, I see. So this squared here is what I dropped. That's why I was so confused. I was like, where is this 2 coming from? There's a squared right here all the way through. So when you take the derivative of this, the reason you have to do all of that, yes. I dropped a 2. Okay. Hold on. Trust the notes. I knew what I was talking about a few days ago. 2. So that's going to be 0 minus 2 times this whole thing, and then we got to take the derivative of the inside. Yeah, I was wondering why there was a 2 magically there. I was like, it's not from the y, surely. And then it's going to be times the, and I need to put a prime there for the, do we need a prime there? Is that a 1? I have a 1 there. Anyway, d over dt of the inside, which is the 16 thing I was just trying to take the derivative of, 100 minus y squared, y1 squared. And let me give myself more room. So that's equal to, or I guess, yeah, I'll keep this part away for now so I have more room to write. So that's going to be equal to negative 2 times 16 minus square root of 100 minus y1 squared times, and that will be, since we can actually take the derivative in here now, that'll be times of 0 minus the derivative of dt of this thing here minus y1 squared, and that will give us 1/2. Let's see, we'll multiply by 1/2, and then the power, so this will give us, this part will give us, it's a minus, right? Yeah, so minus 1 over 2 times 100 to the negative 1, this thing, no, I don't want to keep saying it, to the negative 1/2, and that's times the derivative of the very inside, which will be negative y, I'm just getting rid of the 0 now, 1 squared, and this will be negative 2y1 dy1 dt. So when we throw all of that together, we will have this equation. We'll have 2y squared, or 2y sub 2 dy sub 2 dt, and that's going to be equal to let's see, we have our negative there. So we'll have, I guess this this negative 2 cancels this half, doesn't it? This one. The negatives cancel too. So we'll have, let's see. It says I have one more negative. So we'll have negative 16 minus root 100 minus y1 squared there, and then that's going to be times 100 minus y1 squared to the negative 1/2, which is going to be times this thing here. Oh, this is where the negative comes from. Oh, and we can cancel these 2's as well. Okay. Alright, so we have that right there. Somebody verify that that is correct, this equation I've just written out. Right here. With all of its glory. Can you even see that? Is my face in the way? I'm sorry. Oh, I moved not my face. I moved the iPad. Hold on. Somebody verify that that is the correct equation. While I drink some water and contemplate my life choices. I pulled the iPad too far. This is a travesty. That's good, right? What did I do? I made it smaller. Alright, that's good enough, I think. No, that's supposed to be off the side of the page. Okay. Did we go to 0 viewers? Did everybody just leave because I'm horrific at math? Yeah, it says we went to 0 viewers. Did we drop stream? Did we drop frames? It says I haven't dropped frames. Oh, that was just a mistake on the graph. Okay, it's like everybody just left. They couldn't deal. Okay, I'm gonna operate on the basis that that is correct. Okay, so let's see what can we do with this here. So we know I think it's too far cut off, so I'll just do this on the next page. So we know at y sub 1 equals 6, we have that y sub 2 equals square root of 80, because we calculated that at the start, and that dy1 over dt is equal to negative 2. So let's plug in those initial conditions into our equation. So if I remember correctly, we had y2 times dy 2 over dt. And that is going to be equal to minus 16 minus the square root of 100 minus, is it y1 squared? Yes, and y1 is 6, so it's going to be 6 squared, so minus 36. So that's going to go to 8. And that's times 100 minus y1 squared, so it's 100 minus 36. So that's going to be 64. Those are being multiplied, correct? Yes. Oh, that's to the negative 1/2. That's actually important. And that's times 6 because of this, times minus 2. This is times 6 times negative 2. So let's go ahead and simplify that. So this goes to negative 8, and that's going to be times, so the square root, this will be the negative 1/2, so it'll be square root in the denominator. That's still going to be 8, so it's going to be 8 to the negative 1/2, so that's going to be times, I'll write it as 8 to the negative 1, and that's going to be times 12 from this. And, oh, it's negative 12. Yeah, that way it's a positive number. So that's going to be make all that positive. So these are going to cancel, and that's going to give us 12 is equal to root 80. So we divide by root 80, and we'll get dy2 over dt is equal to 12 over square root of 80. And that is going to be equal to, let's see, with simplification, what can we pull out of root 80? This is 2 times 40. So we can pull out a 4. Can we pull out 2 4s? This is 2 and 20, 2 and 10, 2 and 5. So we have 2 2s we can pull out, so we can cancel that. If we pull out 2 2s, we'll have root 5. So then we'll have, divide this by 2 twice, we'll have 3. So it's 3 over square root of 5 as our final answer. And I sure hope that's an answer choice. I sure hope that's an answer choice. That may have not been an optimal way to solve that problem, but it's done. Assuming that's correct. You can't see my factorization, but you don't really need to see it. Okay, so 2 over root 5 is an answer, no, 3 over root 5. 3 over root 5 is an answer choice, and it is E. So yeah, problem not excessively difficult, just, you know, computationally challenging. That's what we're going to call it. It's computationally challenging. Okay, and that was question 15. And that took a while. Alrighty. So let's go on to the next question. Let's go into question 16. 16. Okay. So 16 is a topology question. Here it is. So we have, you can read it, hold on. I'm starting to lose my voice already. So we have a subset U of R2 is radially open if for every x in U and every v in R2 there exists epsilon greater than 0 such that x plus SV is in U for every s on the open interval negative epsilon to epsilon. So we have if for every x and v that we can construct an epsilon that we can put s on. Oh, I see, like radially open. So like s is on this like radius, this circle of radius epsilon, not including the boundary. And we can pick an x and a v. Hold on, no. Oh, so yeah, so for any combination of the elements of U and R2, we can pick an epsilon so that S with that radius is in U. So then the collection of radially open sets defines a topology on R2. It sure does. Let X be R2 equipped with a radially open topology, and let Y be R2 with the standard topology. Consider the following statements about X. So we want to know which of the following statements are true. Okay. Interesting. I need to look up these definitions here to be able to solve this problem because I don't remember, other than like identity map, I don't remember what second countable and Hausdorff means. So let's do some old-fashioned college studying and Google. So we'll have a Hausdorff. Wow, that was butchered and in caps. Okay, this is not straightened out. Here we go. Hausdorff in all caps for you. So a Hausdorff space is a topological space with a separation property. Any two distinct points can be separated by disjoint open sets. That is, whenever P and Q are distinct points of set X, there exist disjoint open sets U, P, U, Q, such that UP contains P. Yeah. Okay. Basically, we can construct this Venn diagram here around them. We can make two open sets that include the point but don't overlap. Okay, so let's think about this. So we want to know which of the following is true. So is X Hausdorff? X is R2 with a radially open topology. So if you're endowed with a radially open topology in two-dimensional space, can you be Hausdorff? Can you have this open set property that we've got going on here? Yeah, so Hausdorff seems like it's intimately connected with this kind of radially open idea. Because we have, see, it's talking about sets, right? Let me look up this definition again. Hausdorff space is a topological space with a separation property. Any two distinct points can be separated by disjoint open sets. So yeah, it's a separation property. Okay, so let's keep that on the back burner because I don't see like an immediate true or false there. And let's next look up what second countable means. Second countable. Looks like people are already looking this up. In topology, a second countable space, also called a completely separable space, is a topological space whose topology has a countable base. A second countable space is said to satisfy the second axiom of countability. Like other countability axioms, the property of being second countable restricts the number of open sets that the space can have. Many well-behaved spaces are second countable. None of this is as specific as I want it to be. Is this like a textbook screenshot? Axiom countability. Every second countable space is countable. On the other hand, any uncountable discrete space is first countable without being second countable. The continuous open image of a second countable space is second countable. That's just a theorem. A product of Hausdorff spaces is second countable if and only if each factor is second countable. Okay. Yeah, I'm not sure how to go about this one. Is the identity map continuous? So let's go ahead and look at the answer choices. So which one eliminates the most answer choices off the bat? So we've got 1 only, 2 only, 1 and 2 only, 1 and 3 only, and 2 and 3 only. So nothing. Every combination is available except for all 3. So we know that 1 is false, certainly. Let's see. All of these problems have hints, so let's check the hint. Let's go down to hint for 16. Open implies radially open, and this restriction of x to S1 is discrete. What is S1? Let's be reminded here. Yeah, what does S1 mean? Does anyone in chat know what that big S1 is? I might just leave, I'll keep showing you chat, but I might just leave this one for later and think about it. Can we construct two open sets around two arbitrary points here and have them be disjoint? Because of this radially open thing. I don't know, I feel like the fact that the boundary of the radius is open is helpful here. The identity map is continuous. That would be from y, which is the Euclidean, to x, which is our radially open, is continuous. So there's no holes. Yeah, I don't know. I might leave this one for later. Give some time to think about it. I don't think anybody in chat knows either, so let's just move on to 17. Alright, 17 says, let's The group D4 is the group of symmetries of an axis-aligned square in the plane. Suppose the square is centered at 0, 0. How many elements of D4 are conjugate to the reflection over the x-axis? So let's go ahead and get into this one. We will have, whoops, 17. So let's write our formal definition for D4, which I have conveniently written down in my notes. We got that D4 is equal to, oops, this set here, where we have E, R, R2, R3, and then we'll have S, SR, SR2, and SR3. And that can also be written as this. This is just helpful stuff that we're going to use. R and S such that R to the fourth equals S squared equals 1, and RS equals SR cubed. Okay, so what does all that mean? Okay, this says that, so R is talking about rotations. So if you rotate 4 times, you're back to where you started. S is a reflection, and if you reflect twice, you're back to where you started. And this just gives us an operation where we can it just gives us an operation we can use. So in order to see really what the question is asking us is, what is the set, or the conjugate, how many elements of D4 are conjugate to the reflection of the x-axis? So reflection is S. So what is this? So we want to, when we're talking about conjugate, we're talking about of the form, so we need to test elements of the form for some element in D4, let's call it little d in D4, elements that are of the form ds d inverse. So we want to see how many, if we put S in the middle of each of these elements in their inverse, how many, what's generated by that kind of action, and then whatever that set is going to be our answer here. So let's go ahead and write some curly brackets so we can start our set. So let's start, this is not including the identity, obviously, because if you just put the identity in there, it's just going to give you the identity. So let's start by using R. So we'll have RS, and R inverse is R to the third power, because if you rotate 3 times after rotating once, you get back to where you started, or you get the identity. And so what's that going to be equal to? Well, we can use this kind of action here to push our R to the other side, so that we have basically replacing this RS with this SR to the third, but really what we're doing is kind of like pushing it to the other side. And what we'll get from that is SR cubed, which is equal to SR to the sixth, and R to the fourth is the identity, so that will give us SR squared. So that gives us our first element of this set here. Next, we're going to test R squared, so we'll have R squared, SR squared, as R squared is its own inverse. And by the same operation, we can push this R squared over here, and we'll have SR to the fourth, but that's just equal to S, so our second element of this set is S. So this is like 1, 2, 3. We'll try R cubed, so we'll have R cubed SR, but you can see that that's just going to be the same as this one up here, but we can go ahead and do it anyway. Pushing this R cubed over, we'll get SR to the fourth. I guess it's not the same. No, we won't get SR to the fourth. We'll get SRR, that's why, which is equal to SR squared. And then for the next one, that was cubed, we'll just have S but that one's kind of like trivial, right? Because we'll have S is its own inverse, so we'll have S, 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 and these two S's cancel and we just get S. So we've had repeats so far. For 5, we have SR S, oops, S, SR inverse. What's SR inverse? That's going to be equal to R to the third S. So this is equal to SRS R cubed S. And oh, I guess this isn't a good way to write this order because we want our s's to cancel and I don't have to do more operations. So I'm going to start writing the inverses on the left side so I can cancel my s's more obviously. So then we'll have, instead of that, we'll just write SR inverse on this side, S, and then we'll have SR. That way we can just cancel these s's outright. This is still equal to R cubed S, so that will give us R cubed S R, but we've already proved that that is this thing right here, so we get SR squared, and let's do the next one, so that's SR squared, so this is 6, we will have SR squared, oops, should just write that a little better, SR squared inverse S, SR squared, and that will, this SR squared inverse is going to be equal to R squared S. So we'll have R squared S, S, SR squared. These S's are going to cancel, and we'll have R squared S, R squared, but we can see that that is S over here, and we're actually going to have a pattern here if you haven't already figured that out. But let's go ahead and do the last one. Well, the last one is just going to be the same as the first one because the inverses work out that way, but let's go ahead and write it anyway. You'll have S R to the third inverse S, S R to the third. This is going to be RS, S, S R cubed. These S's are going to go away, so this is going to be equal to R, S, R cubed, but that's just this first one here. So that means our entire set here is going to be SR squared and S. And I believe the question asked how many elements are conjugate, so the answer to that is 2. So we have 2 elements, and the answer choice for that is B. So that is the answer to that question. So let's go ahead and move on to question number 18, which I'll put up for you now. So we want to find an antiderivative of 3x plus 11 over x squared minus x minus 6. I'm going to pour myself some more water. Hopefully I don't spill it. Oh, it's very full. I might spill it. It's like all the way full. Just spill it on the stream, and if it cuts, you'll know why. Can I get a rating on my water pouring technique? Chat, are you proud of me? Is there a chat? Is there a chat? Let's see. Hold on. Let me get it back up onto the iPad because this is a relatively simple problem. And that way I don't keep showing you chat. 11 out of 10 water pouring. Thank you. Thank you. It's what I needed to hear. Okay, so this is just going to be basically a partial fractions problem. So we want to take an antiderivative of 3x plus 11, and that's going to be over x squared minus x plus 6 or minus 6. Okay, so we're going to be rearranging this so that we can split it up, and then once we can split it up, it's easy. So first let's factor the denominator here. So that is going to be equal to, or I guess like it's not actually equal to because I have that integral sign there. So that's going to be 3x plus 11 over x minus 3, x plus 2. And so using partial fractions, we want to write that as something like a over x minus 3 plus b over x plus 2, like that. So how do we do that? Well, we want to change our numerator in a way that will factor into parts that will cancel our denominator. So let's note that 3x plus 11 is equal to 4x plus 8, or I guess I should write 4x minus x plus 8 plus 11, not 11, wow, plus 3. So we can rearrange that so that we have 4x plus 8, and so that we have minus x plus 3. Right? That's, wait. No, if we put a minus there, oh, we already have a minus x. Okay, yeah, so it's minus x minus 3. That's what we wanted. I got tripped up by the minus signs. Minus x minus 3, because we have a negative here and a positive there, and we flip them and put the minus there. So that's how we're going to split up our ax and b, so we'll have that be over x plus 2. I guess I wrote them in the wrong order, but it's all good. And this be over x minus 3. No, that's not even correct. The whole, yeah, that's not even correct. So they each have the same denominator. I have to show you what we're supposed to be doing here. So this is going to be x plus 2, x minus 3, and minus x plus 2, x minus 3. Well, we can see that these are going to cancel, and that these are going to cancel and give us a, nope, wrong one. These are going to cancel, and this will give us a constant on the top, so that's going to be equal to 4 over x minus 3 minus 1 over x plus 2. And we're going to be taking the integral of that. So we want to integrate this whole thing, integral of 4 over x minus 3 minus the integral of 1 over x plus 2. Well, what's that going to give us? Well, that's just the definition for log. So we'll have 4 times the log of the absolute value of x minus 3 minus the log of x plus 2. And let us look at our answer choices here to see if that is one of them. And it is not, but because of the absolute value, it is. So if you remember, we have, you can't see it right now, you're looking at the answer choices, but we have 4 times log of x minus 3. And we can flip both of those signs to get 3 minus x and still keep our absolute value, like still keep equivalence there. So our answer choice is going to be equal, or our answer choice is going to be A for our antiderivative there. Alrighty, so let's move on to number 19. Now this one I don't really need to write anything. This is sort of a theoretical question, kind of like the topology one, but I guess with topology you can prove a little more. Let's see what I have in my notes if I did write anything. I did not write anything. Okay, so we have V and W are finite dimensional vector spaces, and that F goes from V to W is a linear map. We want to suppose that for that set of E's as a subset of V, suppose we have a set of E's that's a subset of V, and that F of those E's is a basis of W, and we want to know which of the following are true. So note that basically what we have here is that F is a surjective function. And for 1 is not necessarily true because we have a surjective function, not a one-to-one function. Or it would have to be it's stated to be a surjective function. For that to be true, we would need surjective and one-to-one for each to be a basis. So that means we can limit it to 2 and 3. But which one of those says that we have or that can be verified by surjectivity, and that is the second one, because Because, yeah. No, because... Let me figure out how to articulate this. So... Yeah, because f is a surjective function, it is a right inverse of g. And I believe injective functions are left inverses. So when you have this kind of thing going on where we have these two functions composed with each other, it gives you identity. If it's a right inverse, then this has to be a surjective function. If it's a left inverse, then it needs to be an injective function. I believe that's the correct way to explain it. So that would be 2 only. These two can't be simultaneously true unless we have a bijection, and I believe that that is the same thing for here. We need a bijection for 1 to be true. If for some reason this is a bijection that I don't see, then it would be all 3, I think. But that's not an answer choice, so that already eliminates that right away. So yeah, I'm going with B, 2 only, for number 19. So let's move on to number 20. Number 20 is very fast. So we have find the volume. Here, let me get my page ready. Find the volume of the solid obtained by rotating the region bounded by y equals x to the 4th, y equals 0, x equals 1, about the line x equals 2. So let me go ahead and draw that for you. So I believe x to the 4th, so like y equals x to the 4th, looks something like this. And remember that we have y equals 0 as a bound, so it's just like this big parabola looking like thing. And we have as a limit x equals 1, so let's just call this 1 for the sake of it. 1 from here. So our range is like this, and we're rotating around x equals 2. So this sets us up for the, what's it called? Is it washer method? What is it called? Oh dear. I should know this. It's not the ring. There's the disk method and the other thing. It's the other thing. Someone help me. Someone who's taking calculus 2 before, help me, please. We got 8 out of 10. No. Yeah, somebody help me. It's like, is it the washer? It has like, it's talking about the fact that there's a hole in the middle. Yeah, because we're rotating around this axis, there's a hole in the middle. Anyway, so we can set up our integral like this. It's just a formula. So we have volume equals 2 pi times, and our bounds of integration here are 0 to 1, because we have 0 here and 1 there. And then we have our radius is 2 minus x, as this is like to the left. So it's 2 minus x instead of x minus 2. If it was on the other side, it would be flipped. And then our function, x to the 4th dx. So that's going to equal 2 pi 0 to 1. And then let's go ahead and multiply that x to the 4th through. We'll get 2x to the 4th minus x to the 5th dx. That's just an x. Dx. And when we integrate that, we will get, let's see, we'll have 2 pi times, it'll be 2 over 5 x to the 5th minus x to the 6th over 6 from 0 to 1. Well, we can see if we plug in 0, we're not going to get anything there. So if we plug in 1, that'll be our only answer. So that's going to be equal to 2 pi times, what will that be? It'll be 2/5 minus 1/6, and that'll be common denominator 12/30ths minus 5/30ths, which is 7/30ths, right? Which equals 2 pi times 7 over 30, and that'll give us 7 pi over 15. Is that right? Is that an answer choice? It is. It's C. C. For number 20. Okay, cool. So let's go on to 21. We're making good time here. Honestly, these last few have not been crazy hard. Hopefully I don't make a mistake just going over them really quickly, but if I do, hopefully it's a trivial mistake and you'll forgive me. So let's go to window capture here. We got, so yeah. So yeah. Which of the following are the characteristic polynomial of a matrix that is diagonalizable over the reals? That's a lot of words. So in order for this to be the characteristic polynomial of a matrix that's diagonalizable over the reals specifically, we need to have all real roots. That's basically what we're going to be testing here. So we're going to want to verify if the roots are, if there exists any imaginary roots. So let me get to my notes. Yeah. So to start, I would say if you're going to try to see like if there are any imaginary roots, you want to start by checking the extremely simple roots, especially when you're dealing with something like to the 6th power, which would be awful to try and like solve because it's not really going to be doable unless you can factor out using long division, and that's already a handful. So let's go ahead and write out our first polynomial there and test some really simple complex roots and see if, or imaginary roots, and see if any of them are in fact equal to 0. So we'll have x to the 6th plus 2x to the 5th plus 3x to the 4th plus 3x squared plus 2x plus 1 plus 1. So let's try I. So let x equals I. And then if that is equal to 0, then it's a root, and this is automatically disqualified. So let me bring up my powers of I cheat sheet that I know by heart, certainly. I mean, I actually do, but it's easier to look at it than to think about it for a second, if that makes any sense. So I to the 4th is 1, and then we'll just have I squared, and I squared is -1, so that this will be -1. It's going to be plus. We have x to the 5th, so that's 1 times I, so that's plus 2I. That's going to be plus 3, plus, I guess minus, because that's going to be -1, so it's going to be minus 3, right? Yeah, -1, and then plus 2I. Wait, did I miss a term? Did I just like miss a term in my... 3x to the 4th. Yeah, I'm missing a term. We got 4, oops, eraser, 4x cubed that I missed. Now it's in the front. It's ruining the order. Okay, so this 2I corresponds to what? This part. Okay, so 4x to the 3rd is going to be minus 4I, and then we already did our 2 there, so we have plus 1. So these 1's cancel, these 3's cancel, and this cancels, so we just get 0, which means that it's not 1. So let's see how many answer choices that eliminates. So A is 1 only, so that's not right. C is 1 and 2 only, so that's not right. And E is 1, 2, and 3. So now we have, as answer choices, 3 only and 2 and 3 only. So we should check 2 next, because if 2 is true, then the answer choice is D, and if 2 is false, then the answer choice is B, and we don't have to check 3 at all. Okay, so we're going to solve 2, which is x to the 4th plus x squared minus 2 by using the quadratic formula, but like for quintics, and that's just by setting x squared equal to the quadratic formula. So we have x squared equals negative, did I write that down right? Yes. -1 plus or minus the square root of b squared, which is 1, minus 4 times 1 times -2 all over 2. So that'll give us -1 plus or minus. That'll be -8 minus -8, which is plus 8. So that'll be 3 over 2. And you might be thinking, oh, well, that's not imaginary. There's no I in there. But that's not true, because this is an x squared. So when we have imaginary solutions here. So, for example, if it was -3, then we would have, root square root of negative 4 over 2, which is imaginary. So that means 2 fails, and if 2 fails, then the answer is B, 3 only. And if you don't believe me that like this whole thing works, you can just plug that in and see that that's a root. If you're a skeptic. Alrighty, last one. We spent a ridiculous amount of time doing one related rates problem, and then spent a very little amount of time doing the rest of them. Yeah, Max, thank you. I did drop a term, but I figured it out. I appreciate it. Shell method. Yes, shells. Oh my gosh, I'm sorry. Shell method. I kept saying washer. That's the lame way. Shell method sounds cool, right? Way cooler. Okay, anyway, let's do this last one here. So I'll flash it up on the screen for you. Well, there we go. I'll flash it up on the screen for you here. This is just going to be a differential equation problem. Now, keep in mind, I have not taken differential equations. That's not to say I haven't done differential equations, but I've not taken it. So if I say something stupid or write something stupid, know that that's why. Blame my my lack of classical knowledge on differential equations, but I have done plenty of differential equations types of problems. Anyway, so we have assume y of x solves the differential equation. We have 2xy y prime equals sine of x minus y squared on 0 to infinity, and that we have this this condition for y of pi that is equal to what's it called? Square root of 3 over pi, the whole thing in the square root. Okay, so let's just write out our equation first. We have 2xy y prime, and that is equal to sine of x minus, I believe it's y squared, right? Yes, y squared. Okay, so we're going to make a substitution to start this problem. So we're going to let u equal y squared, that's right. So that means that u prime is going to equal 2u 2u y prime. No, what? 2y y prime. Yeah, I was like, what? 2y y prime. So we can go ahead and substitute that in. So we'll have x, and then this will be u prime. U prime is equal to sine of x minus u. So let's go ahead and rearrange that so we have our terms. Let's just rearrange it so it's prettier, basically. So let's add the u over here. So we'll have x u prime plus u equals sine x, and then we'll divide by x, and we'll get u prime plus u over x. Yes, u over x equals sine x over x. So I'm going to state this as a fact, and we're going to use this to solve the problem. So we have that u prime plus ax u equals bx. So if we have something in this form, which you can see that we do, then u is equal to, I believe it's 1 over alpha times c plus the integral of b of x. I believe that's it. Yeah. And from there, we have that alpha is equal to e to the integral of a of x, or antiderivative of a to the x. So we can see that our a to the x is 1 over x, so that means that alpha is equal to e to the natural log of x, which is just equal to x. So let's go ahead and plug that value in for our alpha there. So we'll have that u is equal to 1 over x times c plus the integral of sine x. Is it sine x or sine x over x? Oh, I wrote the formula down wrong. There's an alpha here. My bad. That's why the x goes away. Alpha bx. So when we put the sine x over x, the x's cancel from the alpha. Okay, that makes more sense. All right, so then we'll have sine x. That's a baby parenthesis. So let's go ahead and evaluate that integral. So we'll have u is equal to c over x minus cosine x. Fix that a little bit. Over x, right? Yes. Okay. So let's see. Where am I going with this? Oh yeah, we got to use our pi now. So remember, because we have this thing for u here, I'm just gonna like draw an arrow. Can you guys see that? Not really. Like down here. Oh, you can't see that at all. Hold on. Like here? That's visible? This, well, you know, I'll just write it somewhere else so it's easier to see for you. So, because we have u equals y squared, some evaluation for, we have this relation, is what I'm saying. So we have, if we plug in a value for u, it's equal to y squared of that value. So basically, we're going to have to take the square root of our evaluation for u here once we plug in pi. So let's plug in pi to this cosine thing here. So we got u of pi is equal to c over x. Oh no, c over pi, sorry. C over pi minus cosine of pi is -1, right? So it'll be +1 over pi, which is equal to c plus 1 over pi. But we know our value for y of pi is the square root of 3 over x. So yeah, so we need to take the square root of that. We're going to solve for c, so we need to take the square root of this. So the square root of, that's still on screen, right? Yeah, square root of c plus 1 over pi should equal the square root of 3 over pi, which means that c equals 2. And I've run out of room completely, even though I did math with no room, so we can finish that off very quickly on the next page. So, let's see, we had u equals, and then we had 2 for our constant, and it was 1 over c minus cosine, so we'll just combine those two and get 2 minus cosine x over x. That's just our definition for u. We want to compute the value of y of 2 pi, so we're going to plug 2 pi into this and then take the square root. So if we plug in 2 pi here, we will have that u of 2 pi is equal to 2 minus cosine of 2 pi is 1 over 2 pi, which is going to give us 1 over 2 pi for our evaluation of u of 2 pi. And then that implies, of course, that y of 2 pi is equal to the square root of that by our original substitution. So that's going to be 1 over 2 pi. And if that's an answer choice, I will be a happy person. It is. That is E. No, it's not E. It's D. That is answer choice D. And that is the last problem on this problem set. So before I go, are there any questions that I may or may not be able to answer about this problem? Oh dear. Let's... Washer method's a different method. Okay. Yeah, I got this formula from Michael. I had to ask for it. Yeah, this is an actual like officially licensed GRE preparation. This is just something made by the University of Chicago to prepare you for the GRE. I actually enjoy the fact that it's probably more challenging than I'll be tested on because it means I'll be overly prepared. I guess it's just the solution you get by multiplying both sides of the integrating factor alpha. Yeah, anyway, so that is our last problem. I am going to head out, but it was good hanging out with you guys. Expect a stream from me on Monday unless more things go catastrophically wrong. But, and forgive if I made any mistakes doing these problems. I'm quite tired today. I had a long week. But, yeah, so hopefully I'll be back at it on Monday, hopefully with fancy stream alerts and stuff. I'm going to aim to live stream by 11, but I do like to procrastinate, so hopefully not any later than about when I started today at the latest. But it was good talking to you guys. It looks like chat was doing really well. It looks like a lot of you guys came by at the back end of the stream. It peaked recently, but it's good to see all you guys. I think some of you are new, so that was awesome. For those of you who may still be here that were new. But yeah, check out the streams. I'll be streaming Monday and Friday. For my GRE prep. Like I said, there are 6 weeks, I believe. Let me check really quickly. For this GRE prep, I'm going to be doing all 6 of them, and then it has practice examinations that I will also be doing, and I'm probably going to try to do those blind. Like, I'm preparing some of these problems and doing some of them live, but I will probably try to do the released tests completely blind. And then if I bomb them, I might do a few more of them prepared until I feel comfortable. But I think I'm going to be trying to take the GRE towards the back end of the year. I think it's offered like every month. Like in this semester, it's like October, November, or whatever, whenever we checked. So, yeah, hopefully we'll be ready. 6 weeks will take us in that kind of time range, so we'll see. But yeah, it was good hanging out with you guys. Look for the stream on Monday if you enjoyed, and I'll see you guys later.